last week. And we were looking at our scattering problem, where the idea is we send plane waves, and there's a scattering center, and after being scattered, it just goes in. It can go in a different direction. That's the kind of problem we are looking at. In fact, most of our measurements are basically scattering problems, most of our observations. And, okay, we define this, yes. We define this T matrix because basically we know that the system we create is far away from the scattering center initially at the beginning of the experiment, and it's also far away again from the scattering center when we are making the observation. So we can basically imagine them to be sent at -infinity, and we make the observations at +infinity. Now, of course, we said that let's just define first them as -t and t. So this U determines the evolution of the state, what we are interested in. We have an initial state, we let it evolve by a long time. During this time, it reaches the scattering center and it moves away from the scattering center. So what is the amplitude that it will be in a given different state? And here we are just denoting them by their momenta. So initially we create a state K, and we ask the question, what happens to this state after a long time? What's the amplitude that it will be found in a different momentum state? And this, well, we just basically looked at a few terms in this expansion of this evolution operator. And since we will be taking time to infinity, we introduced this damping at t equal to -infinity. We are basically saying that at t equal to -infinity, when we create our system, there's no potential. Well, there's no harm in that because basically the system I create is not really interacting with the potential anyway. A more formally correct prescription would be to take wave packages. That is done in, for example, in Peskin and Schroeder, but the result basically turns out to be the same. Because the idea is if your wave is localized into a region larger than a few atomic sizes, it's basically a plane wave. Its momentum is almost definite, especially if it's not at rest. If it has a large momentum, well, basically uncertainty in momentum is practically zero. Relative uncertainty is practically zero. And then we had seen that we could define something called the T matrix. You see, basically this T matrix takes the initial state and transforms it into your final state, scattered state without the initial state. So you see, if you look at this expression over here, we are looking at the S matrix element of U, which is the first term, the Kronecker delta, is no scattering. And then the rest we define as the T matrix. And of course, to come to here, we make the observation that when we have this state, especially when we set the T equals to infinity, all the terms that contribute in the expansion of that time evolution basically have this time dependence. Since all of them have the same time dependence, I just collect all of them and call the coefficient T. And in fact, we had already calculated two of the coefficients, two of the terms in the expansion of T. One is just the potential, the other one is second order in potential, then we will have a third order potential term, etc. And in fact, we also made the observation that we can write this T matrix as in such a form. You see, we obtain this expansion. We rigorously obtain only the first two terms, but it's easy to guess the remaining terms. It's just either V or V propagation and V propagator, V propagator, V. It just goes on up to infinity, and we can just regroup them into this form. So this is the equation satisfied by this operator T. Remember, V is an operator, E is an operator. No, E is a constant, H0 is an operator. And that 1 over E minus H0 is just the operator inverse. And then we define a new state, so-called the psi plus state. Now the thing about this psi star state is this equation over here. Well, basically, psi star's state is our Schrodinger equation, satisfies the time-independent Schrodinger equation with an energy eigenvalue E. And then we said, okay, we can solve this. We could have just as well started from this time-independent Schrodinger equation. And then we could write down a solution of it in this form. Well, there we will still have a problem, because what do we mean by 1 over ek minus h0? The difference between this expression and this expression over here, this one, is in this expression over here, we do have the plus I eta term over there, but in this solution we don't have the I eta. But we have to introduce it in order to be able to define that inverse operator. But in this case, whether we insert the plus I eta, minus I eta, or we use some other regularization, it will change the answer. Whichever one you use will still be a solution of our time-independent Schrodinger equation. All of them are solutions, but they will have, as we will see in a moment, all of them will have a different physical interpretation. They will represent different physical processes.
And the only restriction on eta is?
It will be, we will eventually take it to 0.
Right.
That is a 0.
So it's very small, is the only restriction.
Yeah.
Like,
in fact, all these treatments is valid only in the limit that we take eta to 0. Without eta equal to 0, the solution is approximate, right. But only in that limit, the solution, our steps are correct. Now, of course, once we have let's see, okay, we were looking at this matrix element, and if k and k prime are different, we are looking at different states. Well, the scattering cross-section, now the transition rate, we had already calculated to be 2 pi over h bar, whatever that term appearing times the Dirac delta. Dirac delta is basically, Dirac delta comes from, let me go back. Okay, this exponent leads to the Dirac delta. And, well, of course, you have to, if you remember our discussions before, we first have to keep the upper limit of that integral some arbitrary time t, because we will be taking the derivative with respect to that time t. Then, in that case, when we take the derivative, we take the absolute squared to calculate the rate. And when we take the derivative with respect to t, we ended up having some sine function, sine squared alpha x divided by alpha x, which gave us a Dirac delta. So that is how we had obtained this transition rate over here. So now basically, if we are interested in transition rates to some final states, the task is reduced to calculating this t, whatever that t is. Now, rather than these transition rates, we looked at scattering cross-sections. And scattering cross-section is basically defined as the number of detected particles per second divided by the flux of A particles and the number of target particles. Well, in our case, that is just 1. And hence, we have the, well, let me just go back here. Okay, this is one expression I will be using also later on. So this is the scattering cross-section per solid angle. This is a differential cross-section. And psi plus state is the state that satisfies the time-independent Schrodinger equation. And now we said, okay, so let's look at what this psi plus state is in more detail. So basically, this is the equation it satisfies, which we can convert into, okay, here. This is basically here. This is an integral equation that this state psi plus satisfies. So the next question is, what is that so-called kernel appearing over there? So we wanted to calculate that kernel Well, basically what we did was, since we have the momentum operator in the numerator, but the operator there depends only on the momentum, so we inserted a complete set of momentum eigenstates. So it just turned out to be the Fourier transform given by this expression over here. Now we see, then of course we went to the polar spherical coordinates, carried out the angular integration, and we reduced our problem to a single Fourier transform, an ordinary Fourier transform. Where is it? Yes, over here. This is our Fourier transform that we need to evaluate. Now the question is, what is the physical significance of this I eta? So that basically tells us whether we should insert an, you see, if you ignore the I eta, this function is not, this integral is not defined. It has a singularity. We have to define it somehow. And the way to define it is we have to somehow move the singularities away from the real axis. And then eventually take the limit that they go to the real axis. You see, basically we have two poles. If we insert this I as plus I eta, this is how the poles are shifted. The one on the right is shifted above the real axis, the one on the left is shifted below the real axis. But you can just imagine shifting both poles above the real axis, both of them below the real axis, or shifting the left one above and the right one below the real axis. But eventually we know that this integral, first of all, we have to close it if you want to use the Cauchy integral theorem to evaluate that Fourier transform. That integral will be closed, and it can at most receive contributions from these two poles, which the contribution will be given by the residue at those poles. So we looked at those poles. Basically, the contribution from the poles is, from one of them, it is e to power I k r minus r prime. From the other one, it will be e to power minus I k. Where did I write them? Yes. So here is one of the residues. It has a dependence e to power plus I k r minus r prime. Here, this is the other residue. It is e to power minus I k r minus r prime. And keep in mind that this is a time-independent Schrödinger equation. You can add the time dependence to this. When you add the time dependence, it's e to power minus I omega t. So the first residue, one of the poles has this dependence. The other one has this dependence. This is the time-dependent, if you want, time-dependent solution of time-dependent Schrödinger equation. Now, both of them are solutions of time-dependent Schrödinger equation. But the question is, what do they represent physically? You see here, let me correct this. This is also a minus sign.
Right, that's what I was
Yeah. Now, you see, physically, the first one is an outgoing plane wave. The second one is an ingoing plane wave. So both of them are solutions of our equation. You see, if you go back to this, looking for solutions of, let me go back. We rewrote the time-independent Schrödinger equation, this one. You see, whether I insert a plus I eta or a minus I eta, in the limit eta goes to 0, the psi that I obtain is a solution of my equation. There's no question with that. But those describe different physical processes. So now the task is I already know what kind of a physical process I would like to describe. So that gives me, in a sense, the boundary value that the solution I'm looking for should satisfy. So I'm looking for solutions which I'm sending a plane wave. There's a scattering center, and when this plane wave scatters from the scattering center, I should get spherical outgoing waves. The other solution, when I put instead of plus I eta, if I put a minus I eta, it will basically be an ingoing plane wave scattering from the scattering center into a ordinary plane wave. So that's not the process I'm creating. The process I'm creating is I'm sending plane waves which scatter into spherical waves, spherical outgoing waves. Those solutions satisfy the physical process I'm describing, I'm studying.
So we just throw away the other set of solutions? Like,
Well, you see, you have infinitely many solutions. Both
Yeah.
of them are solutions. So the question is, which one of them are you creating as your initial value? Well, I'm creating the one that has ingoing plane wave, outgoing spherical wave.
is there a system that does the opposite, like where the second set of solutions is useful? Like you have a spherical wave that collapses to a
Well, it will be
center
really,
or something?
it will be really hard to create a spherical plane, spherical waves.
Okay.
Because basically, I mean, if I have an electron gun localized to a reasonably small size,
Right.
not very small, but a reasonably small size, and I'm just sending them to a target.
Mm.
That is basically what I'm describing here. I'm creating plane waves and I'm targeting them to my target, sending them to my target. The other one, well, I don't even know how we would create such a initial state for the electron.
Mm.
Initially, it's spread out everywhere on a sphere, and you are sending them in.
Right.
I don't know even if it would be possible, but mathematically, there's such a solution. If you manage to create that system, such a system, then you should use the other solutions.
And the choice for psi plus is, what's the parameter that labels it plus? Just whether or not it's plus minus?
You see, the plus minus is, you see, here we had already seen that there are two poles, and only one of them. I want this pole. I want a solution which contains the contribution from that pole,
Right.
and not the other pole. Well, that basically tells me that I have to shift that pole into my contour, and the other one out of my contour.
Right, right. So it contributes, it contributes.
Yeah. So that, I mean, my boundary conditions, in a sense, tells me how to shift these poles.
Right.
And in order to be able to do that, I have to add a very small imaginary part to the numerator.
So the state psi minus would be the one corresponding to the second like,
Yes,
projected
yes,
solution? Okay.
yes.
I didn't write that down.
I didn't like the terminology of the book, so that's not what I'm using.
Oh, okay.
Now, of course, there's still the problem, although here I already said that we are closing it, the contour from the positive imaginary part of K, the positive imaginary K plane. That's mainly because this is a positive number. So if I close it from the above the real axis, in that case, there won't be any contribution from the arc from the semicircle that I added. It will not contribute to my integral. So basically that was where we had left. So we had identified our solution. This is what's called the Green's function. And so this is my solution. This is where we had left.
Right.
Of course, well, I'm saying solution, but it's not actually a solution. You see, because what we are trying to identify is psi plus. It appears both on the left and also on the right.
No,
It's-
I have a question. The psi plus is not the final wave function, right? Final wave function after the scattering. We still have to multiply with V.
Well, you see, in fact, psi plus is the whole wave function. It's the solution of the time-independent Schrödinger equation.
So containing before the
Before and after, right?
You see, this is before, this is the one that you are sending. You see, although in the book it starts from time-dependent Schrödinger equation, but eventually it reaches this time-independent Schrödinger equation. But time-independent Schrödinger equation basically describes steady-state solutions. So you can think of it like you are steadily sending electrons, and some of them are scattered. So if you look at the electrons, there is a incoming wave, plane wave, the ones that we are sending essentially, and also outgoing wave. And since it's steady state, it doesn't change in time.
But I'm finding differential coefficients. I mean, in that formula, we have.
Which differential coefficient, sorry?
Above, finding the trans coefficients.
This is the definition we have.
So shouldn't the V and T change place?
Let me see. Yes, you're right.
V psi, okay.
Yes. This is the definition of T. Well, I don't really like it. You see, TK, I can find kind of makes sense because saying that I have the initial incident particle, it's the transition matrix transforming it to the final state. But this V psi, I don't know how to make sense of it.
Because it makes me confused because we start by saying that we have first K and transformed into TK.
Mm-hmm.
But then we say psi plus is the whole wave function, and
Okay.
the scattering coefficient just by looking at the psi plus.
Well, I have a hard time interpreting physically this result. I mean, if it makes sense to you, great. That is why I prefer to add this part here. Basically, this psi plus satisfies the time-independent Schrodinger equation. I mean, in the discussion in the book, I couldn't really make sense of what this psi plus is.
Isn't this just saying the transition operator, T, or whatever, like, is just causing a spatial wave function? Like, you apply the transition operator in momentum space and it gives you the entire wave function in position space? Like,
Yeah, you see, this
there's
is
no dimension.
you see, this is not in position space or momentum space. So
I mean, the K vectors live in.
no, K vector can live in any space you want.
No, isn't this the momentum
No.
representation? Like,
No, this, you see, this is not a representation. This Bryan-Cat notation, basically, it avoids using any representation.
okay, we haven't projected into it.
We haven't yet projected it into anything.
Didn't we define psi plus as, isn't psi plus living in position space? Didn't we project it into
No, no,
position
no.
space at some point?
No. You see, this is the definition given in the book. It defines Tk as V psi plus.
Okay. Where did we define psi plus last week?
Okay, so let's see.
Psi plus appears.
Yeah. Here.
Okay.
We also use the same definition.
We never wrote down a wave function in position space. We never wrote down a wave function in position space.
No.
Okay.
You see, we didn't project it into any space. Well, let me not say space. We didn't project it into any basis in the Hilbert space. You see, momentum, what you call momentum representation is when you project out the wave function, whatever it is, into a basis formed by the eigenstates of the momentum operator. Or when you are what you call the position space is when you project your wave function into a basis or formed by the eigenstates of the position operator.
We work out.
You see, this equation basically implies that H0 plus V psi plus is equal to E psi plus. This, I can't really make too much sense of. This to me means much more than the first equation. They are the same equation, basically.
What happens if you project it into, like, do you calculate the matrix element of, I mean, if you multiply by momentum on both sides, like the bra?
Well, we calculated on multiplying with the position space. We projected in position space over
okay,
here.
right, that's
Yeah.
okay, and we got.
And in fact, that is where we obtained this propagator, this G.
Right.
And then we evaluated it explicitly. And then we found out that the projection of this psi plus in position space
This whole thing, yeah.
is this whole thing.
Incident plus scattering. Incident plus
Yes,
scattering.
yes. And of course, this is not a solution, but it's an integral equation that psi plus should satisfy, and we should solve if we want to obtain an explicit expression of psi plus.
Also stupid, unrelated question, but isn't an integral equation technically a solution to a differential equation? Like one Fedorov equations and like.
Well, I wouldn't call it a solution.
Okay.
They are rather equivalent equations.
Okay.
You see, this integral equation, if you want formally a solution of this Schrödinger equation,
Right.
this one. Or you can also say that this Schrödinger equation is the solution of this integral equation, whichever one you prefer. But none of them are solutions. Some are some form, they're equivalent, but some form is more useful than some other form.
So like Maxwell's equations, like which we convert from differential to integral form.
As we will see, this form, it has the advantage that we can iterate it. Just take this psi plus and insert into the integral. You will get another equation that involves psi plus, but which is also equal to psi plus.
Right.
Take that whole expression and insert it once more into the integral, which contains the psi plus. Each such insertion will increase the power of v by 1, and if v is small in certain sense, you can just cut this expansion at some order.
I think this is just messily done in Sakurai. This is the third time or second time I told you, sitting through these lectures, and everyone gets stuck here because I think it's just not rigorously, like it doesn't give a good explanation for why this happens.
Which
Why
one?
The equation at the top, how to interpret this. Sakurai is not clear either on how we're supposed to interpret this equation.
Well, this is basically what tells me what psi plus
we
is.
sort of knew that at the beginning, right? Like, I mean,
Well, you see, the scattering problem, you can also study the scattering problem in the time-independent case. You see, basically, essentially what I was describing before, like you are sending many electrons, and they will be scattered, so you are creating a steady state. Well, a steady state is essentially, it can be described by a wave function that is time-independent. That's an energy eigenstate. And by the way, E will not be discrete. We are looking for a continuum solution. Because basically E is the energy of my particle when it is far away from the potential. And hence I can write it as h bar squared k squared over 2m.
does reflection and transmittance and all that stuff depend on the form of the potential? Or does it appear here before specifying?
So what do you mean by reflection, transmission?
I mean, where's the probability of something not getting scattered here?
Well, you see, not scattering basically means the final state is k.
Right, okay. K.
Okay, you're done. In fact, we will look at that. The amplitude for forward scattering. It's still called scattering,
Okay.
but the momentum doesn't change.
Does the system, I mean, so what is forward scattering? Is that no interaction with the potential? Like we did?
Now, k doesn't change. It doesn't mean no interaction.
Right, okay.
You
And
see.
an interaction that doesn't do anything. It doesn't change anything. Because the,
Wait a bit.
okay.
Now we will discuss, for example, the Born approximation.
Okay.
And we will see that basically no forward scattering, let's say, is it's possible that there's no scattering. There is one scattering, but still it goes in the same direction.
Okay.
There is one scattering, it changes direction, and another scattering, and it's again going in the same direction. So you say, even if there is a scattering, it might move in the same direction. It can scatter twice, and in between it might change direction, but finally it will go in the same direction. And of course, you can just increase the number of such interactions. So just the fact that it's moving in the same direction doesn't mean it's not interacting.
Right.
Just think about yourself walking on a straight road that's crowded.
All right.
You cannot say that you are not interacting with people around, but you bounce off them and you go straight.
And the fact that the energy doesn't change can't be interpreted to be the same. I mean, the energy doesn't change. K doesn't change.
In forward scattering, K, initial and K and final K are the same.
Okay.
Intermediate stages, K might be different.
Right. Okay.
Other questions? Okay, so let me take this equation from last week. Remember, we are putting everything into a volume of size L cubed. Okay, so this is the equation we have. Well, we can calculate explicitly what this psi plus is, at least when we are making at places where we are making the observation. You see, typically, this is where the scattering happens. You are making an observation somewhere over here. Let's say this is your origin, this is R prime, this is R. So basically, over the region where the integrand is non-zero, that is, the potential is non-zero, within that region, R prime is always much, much less than R. We are observing it from a faraway distance. And what does that mean? Well, let's look at this expression, R minus R prime, absolute value. Well, this is defined as the square root of R minus R prime squared, which is square root of R squared minus R prime squared plus R prime squared minus 2R R prime cosine theta, where theta is this angle. Maybe I should put a theta prime, meaning that it's the theta of the R prime relative to the R, point R, which is equal to R times 1 minus R prime over R cosine theta prime plus R prime over R squared under the square root. And approximately, remember, 1 plus x square root is approximately 1 plus 1 over 2 times x, especially if x is much smaller than 1. Now, whenever you see x is much smaller than 1, so what should be a typical value of x? Can you make a guess?
not small.
Give me a number.
0.001, like
Okay.
1000.
Yeah, that's a very, very small number. But let's see. What is square root of 2?
1.4.
1.4. Well, what is 1 plus 1 over 2 times x? Times 1, sorry.
Oh, 3 by 2.
1.5.
Yeah.
So even square root of 1 plus 1 is approximately not bad. You see, if you take 1 plus minus 0.5 square root, the error is less than 6%. You see, it doesn't have to be
1000.
very, very far away. You see, you have these scatterings that are typically atoms you have or molecules you have, you are looking for. Even if you are at a distance of twice the atomic size or twice the molecular size, well, this approximation is incredibly well.
And in practice, we're very, very far away. Like,
No. Well, in practice, usually you are very far away, but even if you are not so far away, this approximation is still good. So we can use that approximation. Well, I will also ignore r prime squared over r squared. This is approximately r times 1 minus r prime over r cosine theta, or r minus r prime dot r hat. No, let me write it as r prime cosine theta. What I need is k times r minus r prime. This is approximately k times r minus k times r prime cosine theta. Which is k times r minus k prime dot r prime, where I defined k prime as k times r hat. You see, k doesn't change, the magnitude of k. The energy is conserved, we are looking at very long time intervals, so the potential is 0, so there's energy conservation, which means the magnitude of momentum doesn't change, it just changes direction. Now, what is r hat? Well, r hat is this vector over here. So I'm sending my particle in this direction. So this vector is k times r hat is this vector. That's what I call k prime. So now I can rewrite this as e to the power I k dot r over L to the power 3 halves minus 2 pi m over h bar squared L cubed. And this is e to the power I k r. Well, the new denominator, I just replace it with r. And then I have d cubed r prime, e to the power minus I k prime dot r prime, v of r prime, psi plus of r prime.
So what's the constant? 2 by what? Outside?
2 pi m over h bar squared L cubed.
Oh, okay.
That is from,
HK squared.
G. You see, this matrix element, when we calculated it, it turned out that it had that coefficient. Which we can write again as 1 over L to the power 3 halves, e to the power I k dot r minus e to the power I k r over r times all those coefficients and that integral. And remember that integral depends on k through psi plus. Psi plus depends on k. And also on k prime. k prime appears in the exponent. So this is our wave function at points which is away from the region where v is 0. And you can see that here it is also clear that it is a plane wave plus a spherical outgoing wave. Now let's calculate the scattering cross-section. Yes, you remember we defined the scattering cross-section. Well, let me first write this F. This is basically minus 2 pi m over h bar squared L to the power 3/2, because L to the power 3/2 is already out of the parentheses, and I have d cubed r prime e to the power minus I k prime dot r prime, and what is left over here is r prime v psi plus. Let me go even one step further. This is minus 2 pi m over h bar squared d cubed r prime k prime r prime v psi plus, because k prime r prime is that exponent times 1 over L to the power 3/2. Well, now I can calculate the r prime integral. It's just a unit operator. This is my F. Well, we had written the scattering cross-section. Let me find it.
Sorry, how did you do that last step? How did we get to the L and plug in KR?
This step, you mean?
Yes, how do you go from here to the next?
From that to the last line.
No, from the previous to this one, yes.
Yes, from the first line to the second line.
Right.
Well, what is that matrix element, k prime, r prime?
Oh, okay. Under root volume, like.
No, there's no, well, this is,
Yeah.
so that's the only thing I did. Instead of the exponent, I wrote that bracket, the overlap between the k prime and r prime.
Oh, okay, just absorb the L, okay, into that. Okay.
And L to the power 3/2 is already in the definition, in the normalization of that
I was wondering when that
inner
is-
product.
Okay, yeah, that's fine.
Okay, so if you come back to this definition, times h bar squared over 2 pi m squared f k prime squared, which tells me that it's time for a break, because if I had calculated the coefficients correctly, this should turn out to be any questions before you go for a break?